Welcome back to the Deep Dive, the show where we take the most crucial and, let's be honest, often confusing technical documents and distill them into actionable, crystal clear insights that keep you ahead of the curve. Today, we are tackling a really foundational architectural strategy. This is something that is changing how every major organization secures its cloud footprint. We are talking about the concept of going dark. Now, going dark in this context isn't about, disappearing. It's about absolute network isolation. It means moving your most critical, your most sensitive cloud services, your databases, your storage accounts, your key vaults, completely off the public internet. We're talking ensuring that traffic never, not even for a moment, touches an external ISP or a public IP address. It's really the ultimate expression of control. To master this, we've really dissected a dense stack of documents focused entirely on Azure network segmentation, private link, and zero trust mandates. This is the stuff that separates the, let's say, amateur cloud setups from highly secure, compliance-ready enterprises. Our mission today is surgical. We need to fully unpack Azure Service Endpoints and Azure Private Endpoints, the two primary solutions for private connectivity. We've got to identify which one provides true isolation, how to solve the architectural headache that is the DNS challenge, and crucially, why one of these solutions is foundational to a robust zero-trust architecture while the other, well, it leaves a massive security gap. Okay, let's unpack this.
That phrase, going dark, it really does capture the modern architectural mandate, doesn't it?
It really does.
It signifies a complete rejection of legacy network topology where, connectivity automatically implied trust. But before we get deep into the network plumbing of Private Link, we have to ground this discussion in the philosophy that drives it.
Which is zero trust and segmentation.
Exactly. Our sources clearly highlight this definitive shift away from the traditional castle walls approach. For decades, security teams operated under the flawed premise that once a user or workload got past the main perimeter, the castle walls, everything inside was just implicitly trusted.
And that model just doesn't hold up anymore.
Not at all. Not in a multi-cloud remote access world. So zero trust, it just demolishes those walls. It operates on this ironclad principle of never trust, always verify.
Always verify.
Always. It assumes that threats exist everywhere outside and inside your network boundaries. Therefore, trust isn't granted by network location. It's validated explicitly at the time of access based on really three main pillars: the identity of the user or workload, the posture of the device they are using, and the defined role they are executing.
Okay, so if the perimeter walls are gone, how do architects build a new defensible fortress? You can't just have chaos. And that, I assume, brings us to segmentation. It's how we create these micro-boundaries that enforce those zero-trust principles.
Precisely. Segmentation is the strategy for logically dividing your environment to manage and enforce security policies at a really granular level. The guidance is clear. A segment is defined as any logical section of your solution that must be secured as a single unit.
A single unit.
Right. And the strategic architecture dictates how these segments are separated, each with its own specific security requirements.
And this can happen at different scales, right?
Oh, absolutely. You might use Azure subscriptions to isolate entire business workloads from each other. You could use resource groups to isolate application assets within a workload. Or, and this is critical for zero trust, you segment deployment environments, dev, staging, prod, so a compromise in one can't immediately pivot to another.
And you can even go deeper down to the application tiers.
Exactly. Segmenting application tiers, ensuring your microservices database only talks to the application layer and nothing else.
That seems intuitive, but the sources we looked at specify three key security concepts that define those boundaries: perimeter, containment, and isolation. Now, they sound similar, especially containment and isolation.
Yeah.
Can you break down how they function distinctly?
Yeah, that's a great question, and they are distinct. These three elements are really the building blocks of a true defense-in-depth strategy. So let's start with perimeter.
Okay.
This is your entry edge. It is the trust boundary around a segment where you apply controls to block access unless it is explicitly mathematically allowed. It's where you check the identity token, the device health, and the access list.
Give me an example of that.
Sure. So if you have a multi-tier application, the perimeter of the front-end web tier is designed to accept an end user's identity token. But the perimeter of the back-end data tier, that might be configured to reject an end user token.
I see.
Instead, it would only accept a highly privileged specific token that only the authorized application tier is allowed to generate and request. So the perimeter is really what enforces the boundary requirements.
Okay, so perimeter is the entrance exam for a segment. I get that. Now let's tackle containment versus isolation.
Right. So containment is focused on the exit edge. Its primary goal is to prevent lateral movement and minimize the blast radius should a breach occur within that segment.
Limiting the damage.
Limiting the damage, exactly. If a VM is compromised, containment measures like network security groups or NSGs and specific routing rules ensure that compromised asset can only communicate with expected authorized destinations. It's all about limiting the damage after a breach has started.
Okay, and isolation.
Isolation, on the other hand, is the strategy of grouping. It's the practice of putting entities with similar trust levels and security assurances together, protecting them with a unified boundary for ease of management and collective defense.
So like putting all the resources for one application tier into a dedicated subnet.
Exactly that. The VMs, the load balancer, the storage, all in one place. So isolation focuses on creating clean, defined boundaries for management. Containment focuses on preventing unauthorized egress across those boundaries during an active attack. You really need both working together.
I could see how architecturally, if you define the isolation boundaries clearly, your containment rules, like NSGs, become much easier to write and maintain. But I can already sense the operational friction here. This level of segmentation, especially deep microsegmentation, it sounds like a management nightmare. Isn't there a risk that complexity actually introduces more security holes just due to human error?
That is an absolutely valid concern, and it's one of the key trade-offs we have to accept. Look, the strategic benefit of defining a unified segmentation strategy is that it clarifies roles and responsibilities across different teams, right?
Sure, that makes sense.
Everyone knows who owns the production database segment versus the development storage segment, and that reduces human error. However, the trade-off is unavoidable. Complexity and management overhead will increase.
Right.
If you provision separate environments for dev, test, and prod, you inherently increase operational cost. And if you push microsegmentation too far, beyond a reasonable limit, you create an environment that is so difficult to manage that it actually becomes harder to spot real threats.
So the lesson is to segment strategically. Focus on identity as the primary perimeter and ensure least privilege access everywhere. That sets the stage perfectly for how Azure actually enforces this network isolation.
It does. We're not talking about connecting resources inside your virtual network, your VNet, to the managed services Azure provides. Your PaaS services like SQL, Key Vault, and Storage.
And this is where we get into the two main solutions, Service Endpoints and Private Link with Private Endpoints.
That's right.
Let's start with Service Endpoints, or SEs. These were the first generation of private access. What specific problem were they designed to solve?
So service endpoints were designed to address the problem of allowing VNet resources to access PaaS services without, forcing the PaaS service to be exposed to the entire internet. Their core function was extending the VNet's identity to the Azure service.
So you could use VNet-based access rules.
Exactly. It allowed architects to use VNet-based access control lists, or ACLs, to restrict access, saying only traffic originating from this specific VNet is allowed to talk to my service.
Okay, so let's follow the actual network path. If I have a virtual machine, a VM, in my VNet, and I enable a service endpoint on that VM's subnet, how does the traffic change when it talks to, say, an Azure storage account?
Right, this is the critical piece that often confuses people. When you enable the service endpoint, Azure takes control of the routing. The traffic is immediately shunted onto the highly optimized, low-latency Azure backbone network.
So it definitely bypasses the public internet.
It absolutely bypasses the public internet. However, and this is the crucial distinction, the destination address of the PaaS service remains its publicly routable IP address.
Wait, okay, hold on. If the destination is a public IP, how is it considered secure or private?
Yeah.
That sounds contradictory to the whole zero trust isolation goal.
And that is the aha moment that differentiates service endpoints from private endpoints. While the destination IP remains public, the source IP address that the PaaS service sees changes dramatically.
How so?
Normally, if a VM goes out to a public endpoint, it leaves the VNet via a network address translation ANET and presents the VNet's public egress IP.
Right.
With the service endpoint enabled, the traffic path ensures that the source IP seen by the PaaS service switches from the VNet's shared public IP to the client VM's private IP address within the VNet.
I see. So because the PaaS service now receives the private source IP, you can configure its firewall to accept connections only from that specific private subnet range.
You've got it. It's securing access to a public endpoint by validating the source network identity, but the endpoint itself is still technically exposed and listening on a public IP.
So we're securing the doorway by checking the ID of the person knocking, but the building is still on public street. If that's the mechanism, what is the scope of access granted by service endpoints?
Well, the scope is broad, and this is its key security limitation. Service endpoints grant access to an entire service type within a region.
The entire service type.
Yes. So if you enable an SE for Microsoft.Storage in the East US region, every resource in that subnet can now access all Azure storage accounts in East US, provided the destination storage account's firewall allows that subnet range.
That broad access sounds like a massive vulnerability waiting to happen, which I know we'll get into with the exfiltration topic. But first, what were the primary limitations that really pushed Microsoft to develop the Private Link solution?
The limitations are significant, especially for enterprise hybrid environments. So limitation number one, SEs are not natively supported for connectivity originating from on-premises environments, not even if you use express route private peering or a VPN.
So your on-prem traffic still has to hit the public IP.
Correct, which means whitelisting your corporate public IP range, which kind of defeats the purpose of VNet isolation.
Okay, what's limitation two?
Limitation number two, regional constraints, especially for some of the older services. While services like storage support cross-region SEs now, Azure SQL is a notable holdout. It typically requires the VNet and the SQL Server to reside in the exact same Azure region.
Which doesn't always work for modern app architectures.
Not at all. And finally, number three, which is operational but critical, the order of operations. Since enabling the SE instantly changes the source IP from public to private, if you enable the endpoint before you update the PaaS service firewall rules to accept the new private source subnet,
Everything breaks.
all existing traffic immediately drops. This requires precise, controlled deployment and adds a lot of stress during deployment windows.
And service endpoints still ultimately rely on the public DNS system for name resolution, even if the traffic is routed privately.
Correct. The client resolves the public FQDN and Azure routes the traffic optimally, but the fundamental DNS mechanism is public.
Okay, now let's pivot to the isolation champion. The solution that achieves true going dark. Azure Private Link and its functional component, the Private Endpoint. Let's start with the terminology because Private Link and Private Endpoint are often used interchangeably, but they are technically distinct, aren't they?
They are, and that distinction is important. Think of Azure Private Link as the entire framework, the secure global platform Microsoft built that enables this capability. It's the underlying technology that ensures traffic stays entirely on the Microsoft backbone.
Okay, so Private Link is a platform. What's the Private Endpoint?
The private endpoint, or PE, is the actual tangible resource you deploy. It is a network interface, specifically a read-only network interface card, a NIC, that you place directly into a subnet within your virtual network. When you create it, it consumes a private IP address from your VNet's address space.
So it's like a dedicated private off-ramp that brings the remote PaaS service virtually into your private network.
That's a perfect way to put it.
So if a service endpoint is private source IP to public destination IP, a private endpoint enables a fully private internal IP to IP connection.
How did that change the traffic flow?
It fundamentally changes everything. The client application is configured to use the standard FQDN, but thanks to DNS configuration, which we'll definitely get into later, the FQDN resolves directly to the PE's private IP address inside your VNet.
Private IP to private IP?
Private IP to private IP. It completely bypasses any public addressing. And this allows us to take the critical step toward maximum security. You can, and absolutely should, explicitly disable public network access on the PaaS resource itself. And then that public IP is just gone, unreachable.
Exactly, 100% isolation.
This sounds like the architectural holy grail. But the real game-changing differentiator is granularity. How specific can a private endpoint get compared to the regional broadness of a service endpoint?
The granularity is the reason Private Link is worth the complexity. PEs are mapped to a specific instance of a PaaS resource, not the entire service in a region.
So one PE for one specific SQL server.
One specific logical server instance, yes. For Key Vault, one PE maps to one specific vault. And for Azure Storage, the granularity is even finer. And this is a common architectural pitfall if you miss the details.
Oh, interesting. Tell me more about the storage caveat. Why is one PE often not enough for a single storage account?
Well, it's because Azure storage accounts offer multiple services or sub-resources under the same FQDN umbrella: blob, file, queue, and data lake storage, or DFS.
Yeah.
The source guidance really stresses that if your application uses multiple sub-resources, you must provision a separate private endpoint for each required sub-resource.
So if I only provision a PE for the blob service, but my app also uses data lake storage.
Your app will break. Or, worse, it might try to connect publicly. If you only provision a PE for the blob service, but your application attempts to use operations specific to DFS, like managing access control lists, those operations will often be silently redirected by the storage infrastructure to the DFS endpoint.
Which isn't covered by my blob PE.
Exactly. So the connection will fail. Or it might try to connect publicly, leading to a connection timeout if public access is disabled.
That's a crucial failure point. It's not enough to cover the main storage endpoint. You have to consider the specific sub-services your application consumes.
Yes, it's a granular tax we pay for robust isolation. Now, let's talk connectivity. We noted that service endpoints fail in hybrid scenarios. How does Private Link solve connectivity from on-premises data centers? Private Link was engineered specifically to solve this hybrid dilemma. Since the destination address is a private IP inside your VNet, clients connecting from on-premises via ExpressRoute private peering or a VPN tunnel can natively route to it.
No public IP whitelisting needed.
None. No public exposure required. It becomes just another private IP on your enterprise network. Furthermore, Private Link supports connectivity across regions within your own tenant, and even connectivity across different Microsoft Entra tenants.
Which is huge for partner ecosystems.
Yeah.
You mentioned an approval workflow for that, though. If I'm the consumer connecting to a PaaS service, why would my connection request initially show up as pending?
The pending state ensures a critical consent model is followed. If the consumer, your VNet, and the provider, the PaaS resource, are the same entity, the connection is usually approved instantly.
But if they're different?
Right. The approval mechanism is primarily designed for scenarios where one entity exposes a service to another. For example, a company exposing its proprietary API via Azure Private Link service. In this case, the consumer requests a connection, and the resource owner, the provider, must manually review and approve that request before the connection is established.
So it's an extra layer of security vetting.
It's an additional layer of non-repudiation and security vetting, yes.
That makes perfect sense for B2B integrations. Okay, let's synthesize this for the listener. Give us the final verdict comparing these two powerful but very different solutions.
Let's lay the facts out clearly. When you look at Private Endpoint, you are using a private IP address from your VNet. The traffic path is private IP to private IP, providing true isolation.
And the granularity is per instance.
Per instance, exactly. One database, one key vault. Hybrid access is natively supported. The cost, though, involves additional charges per endpoint and for traffic. And the complexity is higher specifically because of the mandatory DNS configuration.
And now for service endpoints.
The IP used is the public IP of the PaaS service. The traffic path is private IP source to public IP destination. The granularity is broad, per service across an entire region.
And no native hybrid access.
No native hybrid access. The cost is, well, it's free of charge. And the complexity is much lower. It's just a simple subnet configuration toggle.
So the best use case for private endpoints is pretty clear.
Absolutely. Critical security, highly regulated data like HiPay or PCI, hybrid cloud deployments, and any situation where data exfiltration prevention is non-negotiable. PEs are mandatory for a strong zero-trust stance.
And service endpoints are best used when?
They are best suited for quick implementation, cost-sensitive scenarios, or environments where traffic is strictly internal to Azure VNets and the security requirements are just less stringent. But architects must understand they are accepting the inherent risk of broader service access.
And that risk brings us directly to the next critical section, data exfiltration. If we're focused on zero trust, we have to assume a malicious insider or a compromised asset exists. Let's define data exfiltration and explain exactly why the service endpoint architecture is so vulnerable to it.
Right. So data exfiltration is the unauthorized movement of data to a location or service not sanctioned by the organization. For example, an employee moving corporate customer data from the sanctioned Azure storage account A to their own personal Azure storage account B.
Let's walk through how that would work with service endpoints.
Okay, let's construct the scenario. Imagine a compromised virtual machine in your VNet that has an SE enabled for Azure storage in West US. Due to the broad scope of SEs, that VM now has a valid network route recognized by the Azure Service Firewall, to every Azure storage account located in West US.
Including the attacker's unauthorized account.
Including the attacker's unauthorized account.
Okay.
So if the attacker manages to gain the credentials, the identity access, to read the corporate data,
The service endpoint provides the necessary network path for the attacker to write that data to their own storage account.
precisely. While the SE ensures the traffic stays on the Azure backbone, it doesn't restrict which destination resource within that service type can be reached. The network boundary itself is just too porous.
And how does the private endpoint provide a definitive network layer solution to this risk?
This is the genius of instance-level isolation. Because a private endpoint is mapped to one specific resource instance, say corp storage account A and nothing else, when you apply network security groups, or NSGs, to the subnet hosting the PE, you can restrict all outbound traffic to only the PE's private IP address.
So any attempt to move data to a different storage account just dies at the network layer.
It fails immediately. There is no defined private route to that unauthorized destination, and, critically, public access on all corporate resources should be disabled. The PE cuts the attack off before it even requires an identity check on the unauthorized resource.
That establishes a really formidable defense-in-depth model. Identity controls determine who can access the data, and network controls via PE determine where they can potentially send it.
And that relies heavily on using your network controls effectively. We need to remember the fundamentals here. NSGs are your stateful packet filters, relying on 5-tuple rule source IP, destination IP, source port, destination port, and protocol.
And for large environments, managing all those IPs and rules manually is a recipe for disaster. That's where application security groups, or ASGs, come in, right?
ASGs are absolutely essential for scaling network management. They're an abstraction layer. Instead of writing an NSG rule that says, allow traffic from IP 10.1.1.5, you create an ASG called web servers, assign your VMs to that group, and write the NSG rule to reference the ASG name.
It's much more readable and easier to maintain.
Infinitely. It reduces human error when IPs change. And regardless of how you manage the rules, the ultimate security best practice must be followed. The explicit deny principle.
Which means?
Your NSG priority list must always end with a low priority rule that explicitly says deny all inbound and outbound traffic.
The catch-all deny.
The catch-all deny. It ensures that any packet not explicitly permitted is blocked by default. Even with PEs protecting the destination, this deny-all rule prevents a compromised asset from moving laterally to other internal resources in the VNet.
So we've established that private endpoint is the superior security choice, but it comes at the cost of architectural complexity. And the biggest hurdle, the one that causes the most headaches for architects, is DNS resolution. Let's dig into that now.
Yeah, the DNS problem is a direct result of Private Link's brilliance. The client application is configured using the original public fully qualified domain name, or FQDN, for instance, storageaccount.blob.core.windows.net.
Right.
But when that client is inside the VNet, it must resolve to the PE's private IP address, like 10.1.1.5. If it gets the public IP and public access is disabled on the service,
The connection just dies.
it just dies. So the FQDN must resolve privately.
How does Azure manage this complex redirection, ensuring internal users get the private IP while external users still get the public IP?
It uses a mechanism known as CNAME flattening combined with private DNS zones. This creates what's called a split horizon DNS.
Split horizon. Okay, walk me through that.
Okay, step 1. When you create a private endpoint, Azure modifies the public DNS record for the PaaS service. It inserts a CNAME entry that points to a special subdomain, which has the prefix private link. So storageaccount.blob.core.windows.net now points to something like storageaccount.privatelink.blob.core.windows.net.
Okay, so the public record is now an alias pointing to this new private subdomain. What happens when my client inside the VNet tries to resolve the original FQDN?
That brings us to step 2, the private DNS zone. You create a dedicated Azure private DNS zone, for example, privatelink.blob.core.windows.net-s, and you link that zone to your virtual network.
The link is key.
The link is everything. Because the VNet is linked, when your client asks Azure DNS for the original FQDN, the DNS process follows the CNAME chain to the private link address. Azure DNS recognizes that domain is a linked private DNS zone, so it looks inside that zone. And inside that zone, there's an A record that directly resolves the FQDN to the private endpoint's private IP.
That's incredibly slick. So the client application never changes its connection string, and it doesn't even know that the DNS resolution was intercepted and redirected privately. It asks for the public FQVN, and Azure DNS just seamlessly hands back the private IP.
Precisely. That's the split horizon effect in action. External users get the public IP, internal users get the private IP.
Now, let's inject the complexity of hybrid cloud back into this.
Yeah.
If I'm a major enterprise with on-premises data centers, coordinating this split horizon DNS was historically a massive headache, right? It required deploying custom DNS forwarder VMs.
It was the Achilles heel of hybrid private link adoption, and it's why the Azure DNS Private Resolver is such a game changer. It's a fully managed Microsoft service that eliminates the need to build, patch, and maintain those custom DNS forwarder VMs. It provides built-in high availability and simplifies the architecture immensely.
Okay, let's dedicate some time to this resolver. What are the two main components, and how do they communicate with the on-premises network?
The private resolver has two components, typically placed in dedicated small subnets within your hub VNet. First, you have the inbound endpoint.
The inbound endpoint.
You can think of this as the receiving dock for traffic coming from your on-premises network. It's assigned a private IP. This is the IP that your on-premises DNS servers must be configured to talk to.
So you set up a conditional forwarder on your corporate DNS server.
Exactly. You create a rule that says, any query for the Azure domain space, like .database.windows.net, should be forwarded directly to the inbound endpoint IP over the express route tunnel.
So the inbound endpoint's job is purely to receive Azure-bound queries and feed them into the Azure private DNS system. What about the second component?
That is the outbound endpoint. This is used for the reverse scenario. It functions like the mailbox when an Azure workload needs to resolve a domain name hosted on your on-premises DNS servers. For example, resolving internal corpapp.local. It forwards the query from the Azure VNet across the express route to your local DNS infrastructure.
Okay, let's trace the hybrid resolution flow for an on-premises client trying to hit the private storage account.
The flow is seamless with the resolver. So the on-prem client tries to connect using the FQDN. Step 1. The client queries its local corporate DNS server. Step 2. The corporate DNS server sees the conditional forwarder rule and sends the query to the Azure DNS Private Resolver's inbound endpoint IP.
Got it.
Step 3. The inbound endpoint receives the query and feeds it into the Azure Private DNS service. Step 4. Azure DNS performs the split horizon lookup and returns the private endpoint's private IP address.
And then that IP travels all the way back to the on-prem client.
All the way back. And the client then initiates the secure private IP-to-IP connection over the express route tunnel.
That significantly lowers the bar for secure hybrid integration. No more managing fragile DNS forwarder VMs. Now that we have connectivity sorted, let's talk topology. In a standard hub-and-spoke network design, where do we optimally place these private endpoints?
Placement is a key strategic decision, and the guidance gives us two clear rules. Rule 1, shared access. If the pay-as resource is meant to be consumed by multiple spoke VNets, a centralized key vault, for example, the private endpoint should be deployed centrally in the hub VNet.
Why in the hub?
It simplifies management, but more importantly, it allows all traffic destined for that sensitive resource to pass through a centralized firewall for inspection and logging. It gives you a single choke point for security.
That makes the hub VNet the security choke point.
Yes.
So what about Rule 2?
Rule 2, isolation. If the pay-as resource is dedicated to and only consumed by a single application, deploy the private endpoint directly into that application's spoke VNet. This maximizes isolation for that specific workload and minimizes dependencies on the central IT hub team.
Makes sense. And there's a constraint for virtual WAN, right?
There is. Ps cannot be deployed directly into the virtual hub. They have to be placed in a connected spoke VNet. So if you need centralization in a virtual WAN environment, you dedicate a specific spoke VNet to act as your security spoke for hosting those shared private endpoints.
That constraint is essential for planning large-scale deployments. Now moving into the highly practical details, let's finish this deep dive with specific configuration nuances, starting with Azure SQL database connectivity.
Right. Azure SQL DB is a perfect illustration of how Private Link introduces a choice between performance and network complexity governed by the connection policy, redirect versus proxy.
Okay, what's the recommended policy?
The default and generally recommended policy is redirect. It offers the lowest latency and highest throughput because the client is redirected to communicate directly with the database node. The trade-off, however, is significant from a network perspective.
How so?
The client VNet must allow a massive, broad range of outbound traffic on ports 1.33 through 65535.
Wait, 65535? That's almost the entire ephemeral port range. As a security architect, opening a firewall for outbound traffic on that huge range sounds fundamentally risky.
It's a function of the SQL backend architecture. In redirect mode, the client is connecting directly to the dynamic IP of the cluster node that hosts the database. And since those nodes can change, the client must be able to initiate outbound connections across that entire spectrum.
So what if my security policy prohibits opening that broad outbound range?
Then you are forced to use the alternative,
Mm-hmm.
the proxy policy.
And what are the trade-offs of using proxy mode?
Proxy mode simplifies the network requirement dramatically. It limits all communication to a single predictable port, TCP 1433. However, you sacrifice performance.
Because all the traffic has to be routed through the gateway.
Exactly, both the control plane and data plane. This introduces higher latency and lower throughput. You use proxy when network complexity is your primary constraint, but you have to accept the performance penalty.
Good to know. So we've configured the VNet, the PE, the private DNS, and the connection policy.
Yeah.
How do we, the security team, rigorously test and verify that the connection is actually flowing through the private path?
Verification is paramount. You can never just assume the PE is working. There are 3 steps executed from an Azure VM within the connecting VNet.
What's step 1?
First, basic connectivity testing. Use tools like Telnet or PSPing to confirm the service is listening on the expected port, typically 1433 for SQL. Run the test using the service's original FQDN. The output should show the tool resolving the FQDN to the PE's private IP address and successfully connecting.
Step 2.
Second, a crucial note. Your application's connection string must always use the service's original FQDN. If you try to connect directly using the PE's raw private IP or the internal Private Link FQDN, the connection will fail by design.
And the final verification.
Third, and this is the ultimate proof, especially for Azure SQL, use SQL Server Management Studio, or SSMS, to run a specific query after connecting from your Azure VM. The query is simple. Select client net address from sys.dmex connections where sessioned at SPNE.
What does that SSMS query tell us?
It returns the actual source IP address that the SQL logical server sees for the active session. If the private endpoint path is active and working correctly, the returned client net address must match the private IP address of your connecting Azure VM.
And if it returns a public IP?
Then the private endpoint path is broken or misconfigured, and the traffic attempted to flow publicly. This query is the final, non-negotiable proof that you have achieved true network isolation.
That SSMS verification query is the kind of practical nugget that makes this deep dive so valuable. Let's wrap everything we've discussed with that powerful case study, the e-discovery company that suffered a catastrophic breach. Why does their story validate the architectural burden of Private Link?
This incident is a textbook example of why the investment in architectural rigor pays off. This company handled extremely sensitive data. They suffered a highly sophisticated, full-scale breach where attackers achieved deep compromise, taking control of their core identity systems, their Active Directory, revoking admin access, and executing a widespread ransomware attack.
Total operational incapacitation, the nuclear option for an attacker.
Absolutely. Their survival was predicated on 2 core architectural decisions, both rooted in the isolation principles we covered. First, they had a robust, highly segmented Azure environment, likely using private endpoints to ensure their critical data repositories were isolated.
And second?
Second, they maintained immutable, air-gapped backups. They had a clean, known good environment state to return to.
And what was the key strategic move during the actual incident response?
They didn't try to clean up the existing environment. That's too risky. Instead, they leveraged their segmented architecture and robust backups to initiate a full recovery of 18 critical subscriptions to a completely new, isolated virtual network structure.
They just abandoned the compromised VNet entirely.
They treated the entire network as disposable, which is only possible with proper isolation and segmentation.
And the timeline. After a catastrophic identity-level breach, how long did it take them to achieve operational recovery in that new environment?
The recovery process, 18 subscriptions restored to a clean, isolated network, took under 36 minutes.
36 minutes! That's incredible.
It's a monumental testament to the power of isolation. It proves that the zero trust investment, specifically in highly contained environments like those enabled by Private Link, provides the ultimate resilience against even the most destructive attacks.
36 minutes to recover an entire multi-subscription environment is almost unbelievable. It shifts the discussion from preventing 100% of attacks to optimizing for 100% recovery. Okay, let's bring this deep dive home and synthesize the core architectural realization for our listener.
The core realization is that the traditional network perimeter is functionally dead in the cloud era. It has been replaced by granular, explicit enforcement. You cannot assume security based on network location.
You have to enforce security using the private link framework for the network path and reinforce it with strong identity controls.
Exactly. Private endpoints are the definitive mechanism for achieving complete instance-level network isolation. They enable robust hybrid connectivity and provide the necessary guardrails against data exfiltration.
They require discipline, especially around DNS, and a cost investment, but they are the non-negotiable foundation for critical environments.
Right. And service endpoints are simple and cheap, but they are fundamentally vulnerable due to their broad scope.
So what does this all mean?
The hard part, the heavy lifting, is often perceived to be the successful deployment of the private endpoint and the DNS resolver. But the security journey doesn't end there. The shift to PEs and zero trust demands continuous vigilance. If you have private endpoints enabled for instance-level network protection, you must continuously audit your identity controls and, crucially, your NSG rules to ensure they match that instance-level isolation. An NSG rule that's too broad, or a user role with excessive access, can entirely bypass the protection offered by the private endpoint. Remember that even when traffic stays on the Microsoft backbone, security is only as strong as the weakest link, which is almost always an overly permissive identity assignment or a poorly maintained network rule. The final layer of defense is ensuring your human oversight matches the precision of your networking architecture.